the Chinese remainder theorem also works if you have three numbers where they are all relatively prime to each other. Here they are all prime, so that's very easy. But if I have three numbers which are relatively prime, the reason why this works by the Chinese remainder theorem is that the Chinese remainder theorem tells me that between the 3 and the 5, the answer to this is x is congruent to something. I don't know what it is yet. Something mod 15. But since I have 15 and 7, which are relatively prime, then between this equation and this equation, those two together will tell me that x is congruent to some other answer mod the product 3 times 5 times 7. I also picked this question because the product 3 times 5 times 7 you will see often. I'll save you some time. I'll tell you it's 105. Okay, good. So now if I wanted to do this, I want to share an extension of the method that we used last time that does this very quickly. When I have three things, now I want to look for an x which has a particular form. And the form has to use the 3s, the 5s, and the 7s. The best format to try is something which involves the 3 and the 5 and the 7. For example, 3 times 5 times a plus 3 times 7 times b plus 5 times 7 times c. This is chosen so that when I look at what x is modulo any of those primes, 3, 5, and 7, a lot of the terms disappear. For example, if I look at what it is mod 3, then x is congruent to the 3, 5a has a multiple of 3, it's gone. 3, 7b has a multiple of 3, it's also gone. And I just have the 5, 7c. And that is what it is, mod 3. So this is telling me that I just need to choose a c which satisfies a nice equation. What equation? I need to have 5 times 7 times c equal to something, mod 3. What's 5 times 7? 5 times 7 is 35. 35 is 1 less than 36. So x is actually congruent to minus c mod 3. Minus c because 35 and minus 1 are the same mod 3. Oh, but I needed to have x to be 2 mod 3. So I just need my minus c. I just need my minus c to be congruent to 2 mod 3. This happens if c is minus 2 mod 3. To make my life even easier, I can choose instead of minus 2, I can choose 1. So already I know what I should choose for the c. C should be 1. That makes me happy because that's a nice small number to multiply by. We can actually finish the rest of the problem just like this too. So let's see at the rest. If I go mod 5, and I don't need much space, so I'll just write it down quickly now. If I want to go mod 5, what's left? The first part is gone. The last part is gone. The only thing left is 3 times 7 times b. 3 times 7 is 21. b is supposed to be congruent to 1 mod 5. But 21 is congruent to 1 mod 5. So this is just b congruent to 1. So let's just choose b to be 1. And for the last part, I need to do 3, 5a. So I'm going now modulo a different thing. I'm going modulo 7. Modulo 7, I have only the 3, 5a. That's 15a is supposed to be congruent to 5. But 15 modulo 7 is 1. So I immediately have that a is congruent to 5 mod 7. So I should choose 5 for my a. So when I look at this all together, what do I have? Actually, because the 21 was 1 and the 15 was 1 and the 35 was minus 1, what this means is that any 3, 5, 7 modular congruence is easy like this. But let's put it all together to finish. Now I have here 3, 5, 5, 3, 7, 1, 5, 7. So now I just have to add these together. And what I see is that 3 times 5 times 5, that is 25 times 3 is 75. Over here I have 3 times 7 times 1, that's 21. I have 5 times 7 times 1, that's 35. If I add them all together, 5 and 5 is, so this is 11 here, and here is 13. So I found out that my answer to this whole thing is 131 mod 105. We usually like to reduce this a little bit smaller. So rather than writing 131, we can reduce 131 minus the 105, and we can also say that the answer to the whole thing is, I could just take 31 minus 5, so it's 26 mod 105. As a final check, since 26 is so small, we can see that it works. 26 is 2 mod 3, because 24 is divisible by 3. 26 is 1 mod 5, because 25 is divisible by 5. And 26, if I subtract 5, is 21, multiple of 7. So this entire problem, even though it looks like it has 3 of these modular congruences, it's actually not much harder than just the 2 modular congruences. The only main idea is to know that you should put this together in this form, where in this form, every one of those terms has 2 of the primes but not the third. That's what causes all of these modular lines to be so simple. And if you think about it, you can probably even do 4. But I'll leave that to you to play with in the future.